Okay, so I was muted. Welcome back. Week 12, actually, it's more than week 12 because we had a midterm in between, but 12th lecture, let's say. Uh, we're going through the end of the semester. We have very few weeks left, two, I guess, something like that. Anyhow, we're going to be doing analysis of variance today. It's an important methodology because it's used very common in many disciplines which uses statistical analysis. Uh, it's really easy to do if you're doing it through a dedicated software, or even if you're doing it via Excel or something like that, or any sort of statistical package. It's a little cumbersome to do by hand, obviously, because there are lots of calculations to be made. But you know me, I want you to do that by hand because it makes you understand what you're doing. Hopefully, all right. Um, I'm not against software packages. I'm not against statistical packages. You're going to be using them in the future, but in order to click buttons, you have to know what those buttons do, or what the type of analysis you choose does. Okay, so you have to have the understanding of the methodology itself so that you can interpret the outcomes and you can just click the correct buttons to do the sufficient type of analysis that you should be doing. All right. So there are lots of variations of analysis of variance. Uh, I'm going to call it ANOVA from now on. It's the universal abbreviation for it, not universal, but global abbreviation for it. Uh, there's ANOVA, there's MANOVA, multivariate analysis of variance. There's ANCOVA, analysis of covariance, MANCOVA, blah, blah, blah. There are lots. And also there is one-way ANOVA, two-way ANOVA, and then it moves on to experimental design and takes you all the way to Latin squares and stuff like that. But you know, I'm not going to be showing you all of those. I'm going to show you just one-way analysis of variance. If you get the idea of what it's doing, uh, I think it's going to be straightforward to understand what multivariate analysis of variance does, what two-way ANOVA does, what uh, adding new blocks, new effects, new sources of variation to an analysis of variance does, and what analysis of covariance does, and so on. All right. Uh, you're just going to have to read and, with what you already know, incorporate the new information and get the hang of it. Okay, whenever you need to. It's always good to understand the basics. Okay, so I'm going to give you the basics. So let's share the screen and get going. Okay, so week 12, analysis of variance. Oh yeah, I said three parts, but then I added one more. So you're going to have four parts today, not four different videos, but four different sections in this presentation and in the whole lecture. I'm going to talk about the general idea. Uh, this is the first time I'm trying this approach, the mostly visual explanation of analysis of variance for the first time. Uh, because I had to explain what analysis of variance is to the MBA class in quality management course, because I was showing them how to do design of experiments, the Taguchi design of experiments for quality improvement, and it makes use of analysis of variance. So suppose you have a bunch of students, 20, 25 students, uh, and almost none of them have no idea about statistical analysis or what analysis of variance is. So I had to give them the basic idea of analysis of variance in a nutshell. All right. So I started thinking, how can I teach this as quick and as simple as possible? So I came up with this mostly visual general idea, and I said, okay, I'm going to start using this in the undergraduate because I think it's going to work. So first, I'm going to make it clear to you, hopefully, what analysis of variance does. Okay, what's the point of it? What's the aim? What's the general logic behind it? And then I'm going to show you the mathematics, how to do the calculations, what they mean. There's going to be new terms. None of them will be new as such. Mostly we're going to be analyzing the variance. So you're going to calculate lots of variation. And then I'm going to show you the analytical procedure, how an ANOVA is carried out. Then I'm going to finish with an example. So we're going to start with the main idea. The main aim of analysis of variance is to test multiple arithmetic means. Okay, so uh, if you have a single sample, right, then you say, okay, I guess the arithmetic mean of the population that this sample belongs to is equal to mu zero. Then you do a single sample arithmetic mean test. It could be a Z, it could be a T, right? Then if you have two samples, then you say, okay, is the population arithmetic mean of this sample equal to the other one? So you test mu1 equals mu2. You don't make an estimation of mu in that case, but you just test the equality of those population arithmetic means. Now, if you have three or more groups, three or more samples, uh, better to say, uh, you're going to be doing analysis of variance, right? Uh, of course, if you don't know how to do analysis of variance, you could do this. Suppose you have four samples, take one and two, sample one and sample two, put them in a two sample arithmetic mean test, Z or T, the last week's lecture, okay? Suppose they are equal, and then take one and three, test those, they seem to be equal. Take two and three, take one and four, two and four, three and four, and then you're going to be doing all the two sample combinations, but that's going to take you six tests carried out one after the other. And the two sample arithmetic mean test is a relatively longer test because uh, before you do the test, if you don't know sigmas and if your samples are not large, then you're going to first have to do a variance test for each of them. And depending on the variance test, you're going to have to decide what type of t-test you're going to be doing and so on. So it takes time, which is not very practical. And remember, you're going to have a 5% error possibility, the significance probability in each of those six tests. So one could have an error here, the other could have an error there, and so on. They could compensate for each other and make you say, okay, all these are equal or seem to be equal, but in fact, they maybe aren't, right? So analysis of variance is a more trustable procedure if you have more than or equal to three groups, three samples, four samples, five samples, it doesn't matter much. And you could ask, if we're testing the equality of means, arithmetic means, why are we analyzing the variance, okay? So I think the most important thing to understand about the analysis of variance is the answer to this question, okay? Uh, we're testing arithmetic mean equality and we're analyzing the variation. Why? Uh, Basically, the answer is simple because all statistical analysis is based on variation, and ANOVA in specific is very clever what it does, how it approaches the equality of arithmetic means problem. You're going to be learning in a few minutes. Suppose this is a data set. Okay, these are the measurements of a quality characteristic of a product, right? So you have a product and it has one dimension. This could be a weight, this could be a length, this could be a hardness, this could be a force before breaking, whatever. All right. Suppose it's a weight or a length. All right. Then you get this distribution. You could see it's not perfectly symmetrical, but it's very symmetrical. It looks very normalish. And this is the aggregate data that's taken from three machines. So we have like 660, 70, close to 700 data points here, aggregated, all right? And this is what we have seen. Obviously, your target value seems to be 100 here, and that's the highest frequency. You have next to it, you have 101s and 99s, and with a less frequency, 102s and 98s, and you see the frequency diminishes as you move away from the center, so it looks very normalish. But in here are 220, 230 samples, each taken from a different machine. So 200 something from machine one, 200 something from machine two, 200 something from machine three, and then we aggregate. Uh, what we're interested in is, are these machines performing equally, right? What that means is, do these machines have the same arithmetic mean for this measure that we're interested in? All right. So if they are, what you're going to be probably doing is, if you're producing similar products. So whatever comes out of the three machines, you could just mix them and then pack them as they come from each machine. But if one machine is significantly different than the others in terms of this parameter, this is a quality characteristic, so it's directly related to customer appreciation, let's say customer happiness, customer satisfaction. I've never taught quality in English, so pardon my lack of vocabulary here. Uh, Customer satisfaction. So you want to have this characteristic as good as possible and as uniform as possible, right? So if one machine is significantly different than the others, if it's worse significantly, uh, then you shouldn't be mixing those products with the other ones, right? Maybe it would be a second grade type of product which would be sold independently at a cheaper price, and so on. So people would pay less and then wouldn't expect the same quality as they expect from the regular price product. Or all right. Or if you have the machine that's significantly different as the better value, suppose going through 105s is better for you, it may not always be the case, right? Having a larger value than the target value may also be not good. Uh, then, but suppose if you're selling vegetables, if you have larger apples, then you could sell them for a more expensive price or something. All right. The the main idea is this: items from three machines mixed up, and they give you this distribution. So in the end of the analysis, we are going to be seeing, as I've just explained, if the three machines perform the same. So based on that, we're going to pack all the items together or not. Maybe we're going to sell items from one machine with a discount or with a more expensive price. So suppose I give you the data from the three machines separately, right? So this is a bar chart, or it's not a histogram, but it looks like a histogram. It's a bar chart, the twin brother or sister of histogram. And the blue bars show machine one, right? Data from machine one. The red bars show data from machine two, and the green bars show data from machine three. Now, do you suppose these three machines, excuse me, perform equally, what would you be looking at? Just look at this graph, maybe pause the video and think about it and say, yeah, they seem to be equal or not. What you would, oh wait, pause, think, give an answer, come back. Okay, what you should be thinking is look at the individual graphs of these three colors, right? Uh, the blue is obvious, so you could just make this curve here, which is like a flatter version of the original. And if you look at those others, this is the most crowded group, and then you have these, and as you go to the sides, the frequencies fall in red and in green, and they all seem to have the same center. Therefore, it looks like these three samples have the same characteristics. Same central tendency, same variation. Is, is it perfectly the same? We don't know. It should be analyzed. But just by looking, you could say, yeah, these seem to be performing equally. Now, I'm going to show you the individual graphs. Let me take my head out of the way, right? So this is machine one. As you could see, the frequencies fall. The highest frequency is close to 80 here. This is 70 something, and this is again 70 something. And the black dotted line is your target value 100. Okay, around this target value of 100, you have these distributions. Do they seem similar? They seem to be similar. Yes, they seem to be perfectly similar, these three data sets. Then you could say, okay, if the samples seem to be perfectly similar, I would expect they are from the same population, right? They probably have the same variance. They probably have the same arithmetic mean. That is what we're going to be trying to say when we're doing analysis of variance. Now, uh, let that be in our pocket and move on. Same data set, same frequencies, same values. Again, this is the aggregate version. This is the, I just copied and pasted the previous aggregate slide here, okay? Same aggregate data, same total data, and with a new uh, distribution of the three machines. So the blue ones are from machine one, the red ones are from machine two, and the green ones are from machine three. Okay? And when you aggregate them, you bring all of them together, you have the same aggregate data graph. But within that aggregate data, their distributions are relatively different. Now you could pause again and think, do they seem to perform well? Should I be packing them together? Pause, think, answer, come back. Okay, let's see the individual graphs once again. My head should be fine here, I guess. Yeah, okay. So this is the machine one. That black dotted line is still the target value 100, right? So this is your machine one, this is your machine two, this is your machine three, right? Do they seem to be performing equally? If you just look at the blue and green, they don't seem to be performing equally. They make up the different halves of the distribution, and the center, the target line, is made of machine two. So we could suspect that these three machines have different performances, and we should probably not mix the final products together and pack them together. Okay, so what is variation got to do with this? All right, so aggregated data did not change, obviously, but the positional concentration of groups within the total data changed. So in one of them, they had the same shape, and when aggregated, uh, it became a more peaked data. And in the second one, you have that peaked total data. Left half is one distribution, right half is one distribution, and center is the other one. So the variation structure changed within the data set. And what do we mean by that variation structure? Okay, so the idea, okay, this is probably new to you, but you're going to learn it. I'm going to teach you well, right? The variation within this aggregate data depends on two things. It is actually made of two things. And if you calculate these two things individually and sum them up, you're going to find the variation here. Not the variance, not the standard deviation, but the variation, because the equality or the phrase here, variation in total data is made of two things, is only true for the numerators, the sum of squares. Uh, because what you divide a sum of squares to get a variance depends on the number of points. And here you have like 600 points, 700 points, something like that. Okay, 670-ish. So you find the sum of squares for this data set and you divide it to 670-ish. And for these guys, you have 200 something for each case. So you're going to probably find a smaller value and divide it to 200 something. And when you sum them up, you may not get the equality, but if you just look at the numerators, the sum of squares, it's going to be true. They're going to be equal. The variation numerator of the variation in this data set is made of the variation within the groups plus the variation between the groups. What is variation within the groups? What is variation between the groups? Okay, so you could see the variation within the groups easily. What we mean by is, if you calculate the variance for this sample, what do? You do x values minus x bar squared multiplied with the frequency, right? Sum them up and then divide it to total frequency minus 1 because it's a sample. But forget about the divided by total frequency minus 1 thing. Just get the numerator. Just get the numerator of this. All xi values minus x bar of this data set squared up, sum up. So that's the numerator variance. We call it sum of squares for dataset 1. Do the same for dataset 2. Do the same for dataset 3. Sum those three up, and then you get the variation within the groups. Okay? For the second case, which we expect the performances are not equal, it's the same thing. Find the arithmetic mean of this data set. Okay, it should be somewhere here, close to that tall bar, all right? So it should be 98 something, close to 99, or between 98 and 99, probably. And xi minus that arithmetic mean squared up for each value, then sum up, then you find the variance numerator for this, which is the sum of squares. Do the same for this one, do the same for that one, then sum up all those three things. And then you get the within group variation. Okay, what is, this is the between group variation. If you calculate, physically calculate that, so if you don't mind, and you're going to get the data set for this a little later on. So if you get that data set, get these data sets, okay, for each case, and then you calculate the arithmetic means and you calculate the sample variances, you're going to find something like this. The aggregate data is an arithmetic mean of 100.06, and the equal performance groups have these arithmetic means 100.4, 100.7, 100.8, where 100.6 is somewhere in the middle of these values, right? In the unequal performance group, you have 98.44, that one, 100.05, 101.68, okay, where 100.06 is somewhere in the middle, very close to this middle group. And if you look at the variances, the total variance in the aggregate data is 2.32. In the equal groups, seemingly equal groups. Variances are 235, 240, 224, which are close to this one. In the unequal groups, we got 0.88, 0.05, which means there's almost no variation here. Does that make sense? Yes, because almost all the data points are at 100. There are very few here, like 5, 7, 6, something like that. Uh, and 0.82. You could see that the variations in these three groups, in seemingly unequal groups, is a lot smaller than total variation, which means in the groups here, okay, in the groups here, there's very small variation within the groups. They seem to be, what does small variation mean? It means consistency, okay? Each group is very consistent in its performance, right? And they don't seem to have the same arithmetic mean at the same time, which tells us that, yeah, they could be different, okay? They have small differences, but they're very consistent in those small differences. Whereas these guys, they have very small variations in their arithmetic means, but they seem to have the same large variation as the original data set. So they seem to act together. Similar arithmetic means, similar variations. These guys, very small variations when compared with the total data set. And even though the differences are small, they have different arithmetic means, and each machine is very consistent with small variation around that uh, arithmetic mean. So, if you just look at the numerators of these variances, what are you going to do? 232 multiplied with the 670-ish something, and it's going to give you a total sum of squares, numerators, variance numerators of 1584 something. Do this for machine 1, 235, 200 something, 220 something, 220 something, 220 something, or 30, thereabouts. Multiply those with the uh, sample size -1 values, and then you get the numerators. You could see that the numerator is 529 something, 546 something, 507 something. They're close to each other, but I don't care about closeness. If you sum these three up, you're going to find the within group variation. The within group variation for the first case where performance seemed to be equal is 1584, 33, 1584, 54. You could see that almost all the variation in the total data is made of the within group variation here in equal performance groups. If you look at the second case, seemingly unequal three machines, okay, 088, again, multiply this by 220 something, 220 something, 220 something, and you get 197, 11.37, 185, 186, something like that. If you sum those three up, you get 394, 395. Okay, so the total sum of squares of 1,500 something, 1,600 almost, only about 400 of that is because of the within group variation here. That means the rest, almost what? Uh, 1,200 portion of this variance is made of between group variance. Over here in the green version, almost 0, 0.21. Okay, 0.21 is between group variation. Over here, 1,200 is made of between group variation. Why is it so? Because the arithmetic means here are very close to each other, one, and the variances are almost similar. So each group is very similar to each other. Therefore, the total variation is made of the variation that is already existent within the groups. But over here, the groups do not have very much variation in them, whereas the arithmetic means are not very close. They could be considered close, 98, 44, and 100.05. Yeah, they seem to be close, but look at these guys. These are really close. These aren't that much close. There's like 1.6, 1.7 difference here, and there's another 1.6 difference here. But what you have here is the highest difference is 0.04. Okay, so yeah, these arithmetic means are far away. There's not much variation within the groups, so within group variation is small and between group variation is large. What is variation? Variation is how your data points are close to the center of the distribution, right? If you take that black dotted line as the center of the whole data set, which is the case, by the way, 100.0, let me see, 100.06, okay? That is where the black dotted line is. And now think of these groups as single blocks, as being close to this black dotted line. Are these groups close to that black dotted line if you think of them as single blocks, single bars? Yes, they are centered and all of them are centered. These guys, this is not centered, this is not centered, this is centered. So there's variation between those groups. I'm going to make that clear. Uh, but first, let's understand the within group variation. Okay, I'm going to show you how these calculations are made, by the way. You're going to understand those too. Uh, so just try to get the general idea here. Uh, Take your three groups, three samples, find their arithmetic means, find their sum of squares, numerator of the variances, right? And sum them up. If that number is close to the uh, variance numerator in the total data, the aggregated data, then probably the arithmetic means of your groups are equal to each other. Mu1 is equal to mu2, and that is equal to mu3, and all of them are equal to each other. If the within group variation is very small when compared with the between group variation, here within group variation is close to 400, and the between group variation is close to 1200, which is about 3 times as large as the within group variation, then you could guess without doing the analysis that the mu1, mu2, mu3 of these three samples shouldn't be equal to each other. At least one of them should be different from the others, or more of them would be different from the others. We could say probably that one, mu1, is not equal to mu3. We don't know if mu1 is equal to mu2 or mu2 is equal to mu3, but we don't care. If that total equality, mu1 equals mu2 equals mu3, if one of them is not satisfied, the whole thing collapses, all right? Because remember your hypothesis. Let's go back and remember the hypothesis. You haven't seen the hypothesis. Here it is. That's your HO. Mu1 is equal to mu2 equal to mu3. Alternative hypothesis, at least one of them is different from the others. So if one of these equalities do not hold any combination, then you just reject the null hypothesis and say, okay, one of them is different, end of the story. They don't have equal arithmetic means. Okay, so uh, remaining total variation, which is the between group variation or variation between groups. You could call it both ways. Basically, if that between group variation is small when compared with the within group variation, then you expect the arithmetic means to be close to each other, because what causes the between group variation is how each sample's arithmetic mean is close to the other group's arithmetic mean. Okay, that is what between variation is. In the first case, the green case, all the arithmetic means are very close, 100.04, 100.07, 100.08. They are very close, so you have very small between group variation. In the other one, 98, 100, or close to 102, there's distance between them. And there's very small variation between the groups. That's also a factor. That's why you're analyzing the variance. So in the equal performance groups, you got between group variation of 1584.13 33, subtracted from the total variation. In analysis of variance, when I say variation from this moment on, I'm talking about sum of squares, not variance. That's why I'm not saying variance, okay? I'm saying variation, and I mean sum of squares. So total sum of squares minus within sum of squares, you get 0.21. Now compare within group variation of 1500, almost 1600 with 0.21, and then compare within group variation of about 400 to close to 1200. Okay, look at these two and look at those two. This is dominatingly a lot larger than this guy. Okay, it's like 6,000, 7,000 times larger than that. And this one is one third, not even two times larger, it's one third. Obviously, the dominating variation here is within group, the dominating variation here is between group. If between group variation is small, arithmetic means are expected to be close to each other. If it is large, then you expect the arithmetic means are far away from each other. That's going to be the basis of your uh, inference, right? So how do you decide whether they are or not? So you get these variations, right? These are sum of squares. Then you're going to, okay, this is one analysis of variance, one case. This is another analysis of variance, another case. So uh, we're learning two problems, two analysis of variance problems simultaneously, all right? So this whole thing is not a single analysis of variance problem. This is one ANOVA problem. This is another example, another ANOVA problem. Okay, I'm just teaching them concurrently so that you understand what the difference is. When is something considered equal? When is something considered unequal or not? Let's focus on this one. You got a sum of squares. You get a sum of squares. Okay. If you divide these by the correct degrees of freedom, they're going to become variances. All right. So if you put the correct denominator below the within group variation, you're going to get within group variance. And if you put the correct degrees of freedom under the between group variation, between sum of squares, you're going to get between variance. For this other problem, same thing, okay? Since we have equal number of data points in both problems, they're going to have same denominators. We don't know what they are, we don't care what they are, but we just know that if I do that, if I put the correct denominator under this and under that, I'm going to have two variances. And remember that slide, it says if between variation is small, arithmetic means are close to each other, which means fail to reject HO. If between variation is large, then I'm going to say arithmetic means are far away. I'm going to reject HO and accept the null hypothesis. Okay? So when will I reject? If between variation is large. Therefore, I will do a variance test between this uh, within group variance and between group variance, but I want to reject when between is large on the right hand side. So it's going to be a variance test that says between variance divided by within variance. Remember, in two sample variance tests, I told you to say, I told you to do the analysis like this. Take the larger variance, put it in the numerator, and always let it be that way. Okay? But that is something else. Over here, because I don't care which variance is the numerator, because there are two samples. I don't care if sample one is the numerator or sample two is the numerator. I want the large one to be the numerator so that I reject on the right-hand side. Over here, again, I reject on the right-hand side, but I reject only if between variation is large. Therefore, between variation is always the numerator in analysis of variance. Okay? And in the denominator, you're going to have within variance. If you reject this F test, two sample variance test, then you reject HO of the ANOVA. Mu's are not equal. Okay, so this is what analysis of variance does. It looks at the variation within the groups, sums them up, looks at the total variation in the data, aggregate data, finds it. The difference between these two is the between group variation. By the way, you can calculate between variation. It's easy. Maybe it's easier than finding within group variance. I don't know. I will show you how to do that, and you will decide for yourself. But if you have total variation, and if you have total if you have within or between variation, you could subtract and find the other one. All right, you don't have to calculate each of them one by one. But if you do, it could be a checkpoint. Okay, I calculate the within variation, I calculate the between variation, I calculate the total variation. Is between and within variation when summed up equal to the total variation? If so, you're probably fine. If not, you made a mistake. Okay, you could do that, but it takes time to calculate all three, right? uh, so you find within variance, you find between variance. Now I'm saying variance because I divided this sum of square and that sum of square to the correct denominators. Those denominators are not as regular as the s square or sigma square that you have seen. It's relatively different. If you remember, when I was talking about sample variance and you divide it by n minus 1, small n minus 1, uh, I said, or I must have said, one of the reasons why you divided it to n minus 1 is because of degrees of freedom. Every variance is a sum of squares divided by degrees of freedom. And in a sample, to find that variance, you have to find the arithmetic mean first. Therefore, to make the calculation repeatable, you deduct 1 from n. So your sample variance denominator is n minus 1. Okay? It's because sum of squares divided by degrees of freedom. In a population, you estimate nothing. Therefore, your degrees of freedom is capital N minus 0. Right? You have to calculate mu to find sigma square, but that calculation is it's a figure of speech. You're not estimating it. Okay? It's a single number, well known. It's a fact. You just find it. In a sample, you estimate mu by x bar. When you do an estimation, that is a minus 1 on your degrees of freedom. All right. So that's that. That's this is what you're trying to do. Between group variation, within group variation, convert them into variances, divide them, do the f-test. If you reject that, reject the analysis of variance, HO. End of the story. So the mathematics. All right. Your data is going to consist of two indexes, two index, two indices, plural of index. Anyhow, okay, let's not open that jar of worms, can of worms. Okay, so you have these I and J. Uh, from book to book, from website to website, from resource to resource, these I's and J's may switch places. Some people call the I samples and J elements. Some do it the other way around. They call J samples and I elements. What do? I call I samples. So if I say X15, that means that's the fifth data point of the first sample. If I say X27, X27 means seventh data point of the second data set. If I say X311, 311, that means 11th point of the third data set, and so on, right? So I is your index for the K groups, and J, this is not I, this is J, the second one. J is the address of the point within the group, right? So we have double indices. One of them shows the group, the sample. The other shows which element you're talking about. All right. So SS total sum of squares, is equal to between group sum of squares plus within group sum of squares. This is a fact. We're interested in the variation numerators. All right. Uh, if you convert these into variances, as I said before, you're going to divide that sum of squares to a correct denominator and that one to a correct denominator. And the denominator of this guy is already known. That equation will collapse. It will not hold. It only holds in the numerator section. Okay. So what is total sum of squares? Obviously, let's go back. If you take that whole data set, find its variance, the numerator of that variance is your SS total. How is that? Take every point, subtract it from, subtract the grand mean. That grand mean is the arithmetic mean of the aggregate data set. Okay. And this is not always the arithmetic mean of the three sample arithmetic means. It's the arithmetic mean of the sample arithmetic means if only they have equal number of points. Otherwise, you have to sum up everything and divide it to the total number of points. Right. So x double bar is the grand mean, the arithmetic mean of the aggregate data set. Basically, it's a weighted mean of the sample arithmetic means. Right. You may have to Google this up. Weighted mean. You basically know what it is, but uh, you might have forgotten. Okay, so every point minus grand mean squared up and then summed up. That's the SS total, right? SS within is the summation of individual sample sum of squares. What is the sample sum of square? It's just the numerator of the sample variance for dataset J. So, sorry, dataset I. So for the first group, first machine, you're going to have SS1, sum of squares 1, which is going to be x1j minus x bar 1. And over all the j, all the points in your data set, you're going to find the squared deviations, sum them up. It's going to become the sum of squares, the variance numerator of the first machine. Do it for the second machine, you find SS2. Do it for the third machine, you find SS3. And if you sum up SS1, SS2, and SS3, you're going to get sum of squares with it. All right? That's it. Sum of squares between. All right. I didn't explain in detail what between variation is, but over here, you're going to actually see it's easier to understand what between variation is by looking at the formula. As you could see, for every sample, machine one, for machine one, you say arithmetic mean of machine one minus grand arithmetic mean of the total data set. You find that deviation, square it up, multiply it with the number of points, number of elements in your first sample. Then you say plus, because it's a summation. You switch I from 1 to 2. Second sample arithmetic mean minus grand mean squared up multiplied by the number of elements in the second sample. Is it done? No. Plus, because it's a summation. You move I from 2 to 3, x bar 3, arithmetic mean of the third sample, minus grand mean squared up multiplied by the number of elements. All right? And if you have more groups, you keep on summing up, which means you do this. Okay. If you're tired, wait for a minute or two before listening to this. How do you find between variation? You do this. You take your sample one, machine one data, replace every element in that data set, in that small sample, okay, with that machine's arithmetic mean. Okay, so if you have, let's go back. If Okay, this is machine one, right? If you have 95, it's not a 95 anymore. It's a 100.04. These 96s, they are not 96s anymore. They're 100.04s, 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 100.04s. How many 100.04s do you have? As many points as here. As many points as here, you're going to have 100.07s, 100.08s. Then get them all together as a single data set and find the variance. This is what that formula does, right? So in the end, you have n1 plus n2 plus n3 plus nk points in your numerator. That means you have the aggregate data set. And each group in that data set is represented by its arithmetic mean. How many times, how many number of points you have in that group, that many times, all right? So that is between group variation. So if your X bars, all of your sample arithmetic means are very close to your general aggregate data grand arithmetic means, you're going to have a very small variation here. And now think of that. If your X bars, all of your X bars are very close to X double bar, that means all X bars are very close to each other. Does that give you support to say if all X bars are very close, then mu's also should be close? Yes. If X bars are far away from each other, what does it tell you statistically? Mu's could be far away from each other, right? This is the basic logic behind the analysis of variance. And it's a this last sentence was important. If you didn't understand, watch it again. Right? If you're testing if mu's are equal, if mu's are equal, statistically you expect X bars to be equal or very close. So if X bars are very close, then X double bar is also very close to them because they are very close, all the X bars. X double bar is somewhere in the middle, all right? So if everything is very close, then you're going to have very small variation here. SS between is going to be very small. Then you're going to say, okay, SS between is small, SS within is large. The total variation is caused by the variation within the groups, not because X bars are far away from each other. Therefore, mu's should be equal. Okay? But if X bars are far away, basically mu's could be far away. Mathematically, what does it uh, result in? The X bar minus X double bar distances will be large. Squared up, they're going to be even larger. Multiplied by the number of data points, they will be even larger. So the total variation will be mostly between group variation, not the variation within the groups, but the variation between the X bars. So you're going to say, okay, X bars are far away, mu's should be far away. An alternative way you're going to see here to find sum of squares of the individual samples. Let me also show you this. You could find it as if you're finding a sample variance numerator, or if you're given the sample variance, you could use this. Now think sample one's variance is something you know, but you need the numerator of it. What is sample variance one? It's the numerator divided by n1 minus 1. Carry the n1 minus 1 over here. If you know si squared and you know ni, you don't need to find that variance, doing lots of operations. Okay, so let's get the formulas related to the visuals I was talking about. That's your aggregate data set. If you find the variance of it, the numerator is going to become sum of squares total. If suppose you have case 2 as an example, you take machine 1 or sample 1, you find the sample variance of this, numerator is going to be sum of squares 1. Numerator of the second group variance will be sum of squares 2. Numerator of the third group variance will be sum of squares 3. If you sum of squares 1, 2, and 3, you're going to find sum of squares within. Good? Very good. And now we represent all these points, all right? All these points in this group, there's like 220 something points in that group. We represent each point with its sample arithmetic mean. We represent each point in this data set with its own sample arithmetic mean. We represent each point in this third data set with its own sample arithmetic mean. So what do you have? You have 220 something 98.44s. You have 220 something 100.05s, and you have 220 something 101.68 or whatever. All right. So you have again 670 data points. You get all these bars together as a single data set, new aggregate data set, which is only made of X bars of the three groups, right? And the center of this is 100.06, the same as before. And if you find the variance of this data set, the numerator is going to be sum of squares between, right? Mathematically, graphically, everything comes together. So that's about the calculations. Part three, by, sorry, and sorry again, the analytical procedure. You start analysis of variance by writing your hypothesis, because analysis of variance is a test procedure, so it starts with a hypothesis set. Null hypothesis, all the arithmetic means are equal. Alternatively, at least one is different, we don't know which. Right. But uh, you don't have to write these down in your analysis. I write these down to teach you. Analysis of variance has some assumptions, and in serious research, we check all these. First of all, data has to be independent between groups, which means if one element is included in one sample, basically you shouldn't be including that same element in another sample. All right? Each elements, all the elements in each sample has to be different from each other, and they shouldn't be affecting each other. That is what we mean by independency. All right? That is case one. That's about the research design. Second, samples should be random. You don't do systematic sampling. Suppose our machine example, three machines, you have three machines. Uh, you take the samples from machine one in early morning only, and samples from machine two in the afternoon, and samples from the third machine in the night shift. And you always do this. This is not a good data input for analysis of variance. Also, it's not a good data input for any type of statistical procedure. All right? Take some from each machine in the morning, take some from each machine in the afternoon, take some from each machine in the night shift. Because based on the time of day, there could be a factor affecting your outcomes, your products. Like, for example, early morning could be, uh, the weather could be slightly cool, afternoon could be hotter, and night shift would be even more colder, and that could affect your outcomes. If you do the previous case, take machine one samples morning, take machine two samples in the afternoon, take machine three samples at night shift, you may think the reason why there's difference in your products is because of the machines, whereas the reason could actually be the temperature, right? You will never be able to see that if you don't take samples from each machine at the same time. So that is what we mean by samples should be random. Third, data should be normally distributed without outliers. There are ways of testing if data set has outliers or not. Uh, I won't be showing them to you in the future. If you need to, you will learn how to do those. And I showed you how you could understand whether a data set is normal or not, but I don't want you to do a normality test. Okay. Uh, Actually, you could do a Yarkebera test. It's not very hard, but I don't want you to do. Okay. But generally, we do it. More practically, we use packages, software packages that does the analysis of variance, and those packages do these checks before they do the analysis of variance, and they present you a report saying, "Oh, your data is not normal. I'm doing the analysis of variance, but your data is not normal, or it has outliers. Clean these first." That type of thing. What if uh, these conditions are not met? Then you cannot trust analysis of variance. Like if your data is not normal, uh, you don't do analysis of variance. You do the equivalent non-parametric test. And I'm not showing you non-parametric procedures. Uh, I think it should be Kruskal-Wallis test or something like that, right? So there are other ways of doing those. If you satisfy these conditions, you could do analysis of variance. And your data should be numerical also, right? Don't do analysis of variance with ordinal scale data or numerically coded nominal scale data. You cannot do it. And the fourth assumption, variances should be homogeneous, which means your samples should have equal variances if you want to do analysis of variance test. What if you don't? Again, your ANOVA outcomes are going to be biased, which is not good. Right. This is very critical. So I want you to test this first. So you first write your hypothesis, then you do an F test, two sample variance test, right? And if you fail to reject that F test, you say, okay, I keep on doing the analysis of variance. I proceed to the analysis of variance. If you fail to reject, sorry, if you reject the equality, okay, if you're in an exam, you're going to do the ANOVA again, but you have to make a note. Variances are not equal. I'm doing the analysis of variance because it's worth 30 points, uh, something, all right? Because even if I give you unequal variances and you say variances are unequal, so I'm not doing the analysis of variance, you lose those 30 points. I want to see how you do it, right? That's the idea. But if you don't make that note, variances are not equal, so I don't know how much I could trust my ANOVA outcomes. You will lose points. Not as much as the case that you didn't solve, but still. And then you calculate everything and you prepare what we call the analysis of variance table. Okay, this is what an analysis of variance table looks like. So in the leftmost column, you have the source of variation between groups, within groups, and total variation. Always in this order, right? Between groups first, within groups. Then at the end, you have the total. Then you have sum of squares, between sum of squares, within sum of squares, total sum of squares. This is a checkpoint, right? When you sum these two up, they should be equal to this one. Then you have degrees of freedom. Okay, degrees of freedom. You have k groups. Suppose you have three groups, then your group's degree of freedom is 3 minus 1, which is 2. Okay, fine. Simple as that. If you have k groups, degree of freedom is k minus 1. Total degree of freedom, also easy. If you have n points, total degree of freedom is n minus 1. And as your sum of squares, when summed up along between and within, should equal to total, it's the same case for the degrees of freedom. When you sum up between and within degrees of freedom, they should be equal to total degrees of freedom, which is n minus 1 minus k minus 1 is going to give you an n minus k. The idea here is simple. Actually, within groups is the variation in each group. So first group has n1 minus 1 degree of freedom. Second group has n2 minus 1 degree of freedom. Third group has n3 minus 1 degree of freedom. What do you have now? n1 plus n2 plus n3 minus 1 minus 1 minus 1, which is capital N minus 3. total number of data points minus number of groups. All right. If you try to memorize these, okay, you may forget. Just just learn. Okay, don't memorize. Learn. I have 100 data points, then total 100 total data points, then I have 100 minus 1 degrees of freedom. Period. Okay. I have four groups, then I have 4 minus 1, 3 between group degrees of freedom. And 3 here, 99 here, then this should be 96. Period. I don't want to see formulas. I want to see correct solutions. Right? If you learn this way, life is easy. If you try to memorize n's, k's, everything is going to be, there's a chance. It's not going to be for every one of you, but there's a chance that they will all be mixed up. Then you have the mean squares. What are mean squares? Average sum of squares, which is actually the same thing as variances. Okay, these are your between and within variances. You get that sum of squares between divided to its degree of freedom, then you find its mean square, you find its variance. You get the sum of square within divided to its own degree of freedom, then you get the sum of variance for within group variation, variance for within group variation. You don't have to find the same thing for total. We don't care about the total anymore up after this point because that's not a checkpoint, basically. Then you have the calculated F. You're doing a two sample variance test between variance divided by within variance. So mean square between divided by mean square within. That's your calculated F. Then you have the F table value for comparison. All right, from the table with between and within degrees of freedom. It's of course between and within degrees of freedom means these numbers k minus 1 and minus k. So if this is 3 and 96, you're going to go look up from the F table 396. Generally do this test with a 5% significance table. All right, 5% is fine. You could just use that. If your table value is larger than your calculated value, this is a fail to reject. Between variation is not significantly larger than within variation. That's fine. Mu's could be equal. If your between variation is significantly larger than within variation, that means sample arithmetic means are far away, then mu's should be far away, and it's going to be a reject. If calculated F is larger than table F, you will reject HO, end of the analysis of variance. Good. So, part 4, example. From our 3 machines, I take 10 samples from machine 1, 9 samples from 10 samples from machine 1, 9 samples from machine 2, 12 samples from machine 3. Fine. I didn't take equal number of values. And I want to check if they perform equally. I hope to measure 100 grams per package, and this is my data set. Okay, first, without doing anything, let's look at the data set. I won't give you graphs here. I just give you calculations. You may draw your own graphs if you like. So we got 95, 97, 95, 98, 97, 96, 100, 97, 98, 94. Average of this is 97-ish. 97, 99, 100, 101, 97, 100, 300, 97, 99. Average of this is 98-ish, I guess. 100, 100, 300, 499, 100, 98, 103, blah, blah, blah. This is 101-ish, somewhere over there. Then I find the arithmetic means. Okay, 96.7, 99.33, 101.33. Now, when you find these sample arithmetic means, or if you have these sample arithmetic means, you could simply find the total arithmetic means. If you sum these 3 and divide it to 3, you're going to see it's not equal to this one. This is something else. This is 96.7 times 10 plus 99.33 times 9 plus 101.33 times 12 summed up divided to 10 plus 9 plus 12. It's the weighted average, right? So that's your weighted average. Then I find the sum of squares. This is where I find the sum of squares. This is how I do it. 95 minus 96.7 squared, 97 minus 96.70 squared, and so on for sample 1. Then I sum them up. I get sum of squares 1. Then 97 minus 9933 squared, 544. 99 minus 9933 squared, 011, and so on. I do this for second sample. I find sum of squares 2. I find sum of squares 3. Then I don't sum these up yet. I find sum of squares total. How do I do that? I get the grand mean. This is x double bar, okay? Total mean, x double bar. I do this. 95 minus 99.26 squared, that. 97 minus 99.26 squared, that. 100. I do all these deviations with 99.26. Then I do all these deviations again with 99.26 in the second column. The same in the third column. Then I sum up everything. Then I find the sum of squares total. Good? Good. I may need sample variances. I will need sample variances because I will do a two sample F test to see if samples have equal variances. So 28.10 divided by 10 minus 1, 36 divided by 9 minus 1, 46.67 divided by 12 minus 1, 11. Okay? I find sample variances. Now, the largest sample variance is 450, the smallest sample variance is 312. I will do an F test between these two. If I fail to reject, I can proceed with the analysis of variance. So I open a parenthesis in my analysis of variance and I say, is variance 1 equal to variance 2 equal to variance 3? Alternatively, at least one is different. How will I do that? I will get the largest one, which is variance 2, and the smallest one, variance 1, s squared 1, 2, divided by, this is not sigma, this is s squared 2, okay, that guy, s squared 2, divide 144, go to the F table, 5% F table, 8, 9 degrees of freedom, why 8, 9? There are 9 points here, minus 1 is 8. There are 10 points here, minus 1 is 9. So 8 numerator, 9 denominator degrees of freedom. It gives me 323. Calculated F value is 144, smaller, closer to 0. This is a fail to reject. They seem fine. So if I reject, I fail to reject the equality between largest and smallest. The third one is going to be somewhere between them, no problem. If you like, you could check, but there's no need. Uh, Proceed to analysis of variance. So I had previously found, okay, back to here. My hypothesis, I had found SS1, SS2, SS3. Now I will sum those three up to find SS within, which is 110.77. I already have 227.94, which is the total sum of squares. So you could just subtract, subtract 110 from 227 to find the between group variation, which is 117.70. Okay, this is one way of doing it. The other way, if you want to work the between group variation formula, you could do this. Ni for each sample size, sample arithmetic mean minus general mean squared up. So you get 96.70 minus 99.926 squared up. How many times? 10 times, because I have 10 points here. 99.33 minus 99.26 squared up. How many times? 9 times, because I have 9 points here. The same for the third sample. 101.33 minus 99.26 squared up multiplied by 12 points, 12 times. If you sum them up, you get 117.1688, which is already very close to 117.17, just rounded up. That small difference, no problem. So now you have SST, you have SSB, you have SSW, you have degrees of freedoms. there's no reason why you shouldn't proceed to the analysis of variance table, right? So between group sum of squares, 117.17, within group sum of squares, 110.77. Total group variance, write it here. This is your checkpoint. Sum these two up to see if total is fine. All right. I had three groups, so 3 minus 1, 2 degrees of freedom for the between groups. Okay. I had 31 data points, minus 1, 30 degrees of freedom for the total. You could just say 30 minus 2, 28 is the degrees of freedom within groups. Or you could say this 10 minus 1, 9, 9 minus 1, 8, gives you 17. 12 minus 1 for the third group, 11. 17 plus 11 is going to give you a 28. Or total number of points minus number of groups, 28. Same thing. So move to mean squares. I'm converting sum of squares to variances. 117.17 divided by 2, 58, 58. 110.77 divided by 28, 396. Now, this is the funny bit. Because of these degrees of freedom, you're going to see that even if between groups is slightly larger here, since the within group variation is generally divided into a larger degrees of freedom, it becomes a lot more smaller in the end. And the between group variation is a lot larger, remains larger. So divide mean square of between groups to mean square of within groups, 58, 58 over 396, you get a calculated F of 1481. You go to the F table, 95% or 5% significance F table, okay? Numerator degrees of freedom 2, denominator degrees of freedom 28. It's going to give you the F value of 250. Calculated F is larger than the table value, reject HO. These mu's should not be equal to each other. Right? And that is analysis of variance for you guys. I hope you enjoyed it. Please subscribe to my channel and don't forget to hit the like button. Yeah, I don't expect you to do that, but I'm posting new videos, music videos, so you could subscribe if you like. And me and my friends, we got this new YouTube page, Gallows Pole. That was my high school band. I was like 15 or 16, 15 when we started playing together. And after 30 years, we started playing again. So you could go check. Your friend Ibrahim plays the keyboards with us. Hi, Ibrahim. Uh, he's very good at that. So uh, yeah, keep healthy, keep happy, keep positive. Okay. I know you get mad with me sometimes. Some of you do. I still love you. I still love you. Right? Uh, just be fine. Life is too short to become angry at everything. Right? Be positive. Bye.